So, the plan for today is to prove Stirling formula, which is an approximation of the factorial by means of elementary functions. And to achieve this, we also need to prove the Wallis product, which is an infinite product converging to pi over 2. So the plan is first to prove Stirling formula up to a constant. So we are going to prove that n factorial is asymptotic to some constant c times square root of n to the power n divided by e to the n. And here, of course, we mean an is asymptotically equivalent to bn, means that the ratio an over bn goes to 1 as n goes to infinity. So first we prove Stirling formula without finding the exact constant c, and to find c we need Wallis product, and so we are going to prove also Wallis product, and at the end we'll have the full Stirling formula. So let's prove Stirling. Stirling approximation. Okay, so the idea is somewhat very simple, because the idea is that n factorial, if we make the logarithm, this is the logarithm of the product, is the sum of for key which goes from 1 to n of the logarithm of key. And the idea is that this is the sum of the logarithm can be approximated with an integral. So the idea is to consider this integral, the integral from 1 to n of the logarithm of x in dx. This we can solve. We know that the antiderivative of logarithm is x log x minus x. Okay, check it. You make the derivative of x log x, you get 1 times the logarithm, so this is the logarithm. Then you get x times the derivative of log x, which is 1 over x, so 1 minus the derivative of x, which is 1, so 1 cancel out, and this is the antiderivative of logarithm. This must be computed between 1 and n, so you get n log n minus n minus the same computed in 1, the logarithm of 1 is 0, so you get minus 1, so plus 1. This is exact, and however we can approximate this integral. We can approximate this. What are we computing? Let's make a plot here. We have the logarithm, which is something like that, and the idea is that we can subdivide, we can consider the integers here and approximate the area, which is the integral of the logarithm, the area below this curve, with trapezoids. So from below we can approximate the area by taking the the second the chords of this subdivision, and okay, this is the logarithm of 2, logarithm of 3, and from above we can take the tangent here, the tangent trapezoids. So this will give a very precise approximation of the integral, and these two approximations, in particular the one from below, will produce the n factorial we are looking for, and the one from above we need it to compute the error between the two, and so get an approximation formula. This is the idea, so let's go on. The approximation of the integral goes like this. Okay, let's magnify one small interval here. In general, if you have a concave function, in general you have any convex function y equal to f of x, and you want to compute these two estimates from below with the chord between the two endpoints, and from above by means of the tangent line in the midpoint of the interval. So this is tangent in the midpoint, and of course if f is concave, it's clear that the integral of f in the x in this interval can be estimated by above and by below with these two linear functions. So from below we get the integral of the green linear function, and this integral is equal to what? So we are computing the area of this trapezoid, and this area is clearly equal to the area of a rectangle. So the idea is this. This is equal to the area of a rectangle which has the same basis and has height, which is the average of the two heights of the trapezoid. So this is equal to b minus a times the average, so fa plus fb divided by 2. This is the green area. On the other hand, the area below the purple line, which is the tangent line in the midpoint, this is equal, since this line is in the middle, the area is equal to the area of the rectangle, again the rectangle which has height equal to the value in the midpoint. So from above we get again b minus a, b minus a, and here we have f in the midpoint, a plus b divided by 2. This is true in general for any concave function. Okay, so we can plug in our logarithm and take the interval between two integers, and we get that the integral between k and k plus 1 of the logarithm of x dx can be estimated from above, from below, with b minus a is equal to 1. So here we have the logarithm of the average, so k plus 1/2, and here we have b minus a is 1, we have the logarithm of k plus the logarithm of k plus 1 divided by 2. Okay, so the estimate on the left is the one we will use, and the estimate on the right, we only need to have an estimate on the error. So the idea is to say that the integral of the logarithm is equal to the quantity on the left hand side plus an error which we can call a, or let's call it epsilon k, and we know that this error is positive, of course, and is less than the difference between the upper and lower bound. So this is less than the logarithm of k plus 1/2 minus the logarithm of k plus the logarithm of k plus 1 divided by 2. And now we are interested in finding some approximation, some asymptotic of this epsilon key, and so we are going to make an approximation of this formula. So remember that the logarithm of key plus 1/2 is equal to the logarithm of key, collect key, so we have 1 plus 1 over 2 key, and this is equal to the logarithm of key plus a small error, which is the logarithm of 1 plus 1 over 2 key. And the same is true for logarithm of k plus 1, which is logarithm of k plus logarithm of 1 plus 1 over k. And remember the Taylor expansion of the logarithm says that logarithm of 1 plus x is equal to x plus something of order x squared. Okay, so what we get is that epsilon key is positive and is something like you see, just plug in, we have logarithm of key plus, we use this formula here, so plus, and you use also the Taylor expansion, so we get 1 over 2 key plus big O of 1 over k square, and then we have minus divided by 2 logarithm of key plus, and again we use now this second formula here, so here we have used the green one, and now we use the red one, and we get logarithm logarithm of key plus 1 over key plus big O 1 over key squared, and this is the red formula. In the end, this simplifies. You see that the logarithms of key simplify. This one simplifies with the sum of these two, which are divided by 2, and so we and also you notice that also the first order terms simplify, and so we get order of 1 over key squared. This is the only information we need, because recall that this is enough to say that the sum of epsilon k, this implies that the sum is convergent. This is the sum of positive terms, the series. This is equal to some constant. Let's call it okay, epsilon. Convergent, real number. Now this is so what we have got. Let's start again. We have this formula for the integral of the logarithm. Start from there. We have so the formula was n log n minus n plus 1. Just check it. Yes, this is equal to the integral from 1 to n of the logarithm of x dx, and this is the sum for key which goes from 1 to n minus 1 of the integral between key and key plus 1 of the logarithm of x in dx. So we have divided as in this picture, and then the picture here on the right, and every integral we have make the approximation, and we have found that each one of these, so we have the sum, each one is equal to this formula here, which is the logarithm of key plus the logarithm of key plus 1 divided by 2 plus epsilon key. And now we have what we have. Okay, let's now divide this series. So we have 3 terms. 1 half the sum of logarithm of key plus 1 half the sum, the same thing but shifted. So we start from 2 up to n, and we have the logarithm of key again, plus the sum of epsilons. And now we can put together these two sums. So this is the sum of the logarithm from of key from 1 to n, but we are missing a term here, so we have to remove 1/2 logarithm of n. Okay, because we are missing here the last term. Here we are missing the first term, but this is 0 because logarithm of 1 is 0, so this is not a problem. And so this is what we get, and here we have this error. And basically we are done, because this is, as we said before, the sum of the logarithms is the logarithm of the product, and the product of the numbers from 1 to n is n factorial. So here we have the logarithm we are looking for. And now we have only to resolve for it, and we get what we get is that we solve for the logarithm of n factorial, and we get that this is equal to this formula here, which is n log n minus n plus 1, and then we have to subtract this, so plus 1/2 logarithm of n minus the sum as k goes from 1 to n minus 1 epsilon k. And now what we have, take the exponential of both sides, and we have that the logarithm of n factorial is equal to e to the n log n divided by e to the n times e to the power 1 times e 1/2 logarithm of n divided by e to this power, and this is equal to e to the n log n is nothing else than n to the n, e to the 1 is e to 1 to the power log n is of course n raised to the power 1/2, this is the square root of n, and here we have e to the n, and here now, so this is exact, but here now we know that this is going to, this is equivalent to the limit of, if we replace this with its limit, which is nothing else, since the series is convergent, this is e to the power epsilon. So we have that this is what we were looking for. There is a constant c, which is e, let's say e divided by e to the epsilon, and then we have the square root of n to the power n, e to the n. This is what we were looking for. So the constant, we don't know what it is, but it is a finite constant, and we have the formula we were looking for, this one. Okay, so how do we find the exact value of this formula? We need to prove, we are going to prove this Wallis product, which is a totally different story, and in the end we will use this formula. So the idea is, you see that here there is something related to the factorial, and so we will be able with this formula to find the asymptotic constant of the factorial. So assuming this formula is true, which we have proven, by replacing this formula in the Wallis product in some way, we will see, we will be able to relate C to pi over 2, and so find the exact value of C. So we are going to prove Wallis product now. Okay. And this is a totally different story. Okay, so the idea is this. Let's take this integral in, the integral between 0 and pi of the sinus of x to the power n. So let's draw a picture. Here we have the interval 0 pi, and we have the sinus here. So this is sin of x, and then we have the powers of this. So we have sinus square is something like this, and then sinus cube. All of these are positive because in this interval the sine function is positive, and in pi half all these functions are equal to 1, but in every other point they are less than 1. So when you rise to the power n, they go to 0. These functions become very close to 0. In particular, since this is decreasing in n, sine of n plus 1 of x is less than or equal to sine n of x, simply because these numbers are between 0 and 1, so they decrease when you make the power, so in is decreasing. This is positive and decreasing. You could prove that this is going to 0, in is going to 0, but we don't need this, because the idea now is the following. Let's compute we want to compute these integrals. So I0 is the integral between 0 and pi of 1. Sine to the power 0 is 1, and this is pi, while I1 is the integral of the function sinus of x, which is of course minus cosine between 0 and pi, and in pi we have minus 1, so 1 minus and in 0 we have 1, so we have to sum both and find that this is equal to 2. And now we notice that we can compute in by induction, by integrating by parts. So if you have, for example, sine squared, you can integrate it by parts. And in general, if you want to find in plus 2, for example, this is equal to the integral between 0 and pi of sine to the power n plus 2, which is sine to the power n, times sine to the power 2. But now we can write this. We would like to have a cosine here, so to make an integration by substitution. So we write sine squared has 1 minus cosine squared, and so this is equal to the integral of sine to the power n that we suppose we have already computed. So we are looking for an iterative formula, so this is good for us, and what remains is the integral of sine to the power n of x cosine squared, which we can write like cosine n cosine n dx. We write like this because now this is going to be, this looks like the derivative of the integral of the derivative of sine to the power n plus 1. So this is this can be integrated, and this can be differentiated, and so we can use the formula of integration by parts. So the first term, this one, is in. We suppose we know it, and here we have just look, so what is the derivative of sine to the power n plus 1 of x? The derivative of this is n plus 1 sine to the power n of x times so times the cosine of x. So up to this constant here we have, so we have 1 over n plus 1. Here we have the derivative of sine to the power n plus 1 of x, the derivative, and then we have cosine of x. This is an x. Dx. Okay, so we can integrate by parts. This is I1 minus 1 over n plus 1, and here we have by parts sine to the power n plus 1 of x times cosine of x between 0 and pi minus the integral of, so here above we have the derivative of this term, and so here that term is left as it is, and we have to put the derivative of the cosine, which is minus sine. Okay, this is between 0 and pi. Okay, so in minus 1 over n plus 1, and now notice that in 0 and in pi the sinus sine is 0, so this is going to this is cancelled, and here we have minus minus, so plus the integral, and here we have the integral of sine to the power n plus 2 again. But this is good because we have what we are looking for is equal to what we know minus a small amount of what we are looking for. So we can solve in I n plus 2 and find it. So we find that in plus 2 is equal to so let's so we have 1 plus 1 over n plus 1 in plus 2 equal to in, which means that we have this recurrence formula. In plus 2 is equal to, so this is 1 over 1 plus 1 over, so let's write it this differently. This is n plus 2 divided by n plus 1, right? So this is n plus 1 divided by n plus 2 times in. This means that in plus 2 is equal to n plus 1 divided by n plus 2 in, but in is equal to, again, let's plug in again in this formula, and we have to decrease the numbers by 2. So here we have n minus 1 divided by n, and then we have in minus 2, which is n minus 3 divided by n minus 2, and so on. And at the end you get I0 or I1, depending on whether n is even or odd. And this is very, very nice, very strange and very nice, because I0 is pi here, while I1 is 2. So we get two very different last terms, one involving pi and the other one not involving pi. And the idea is that when n is very large, these terms here should be asymptotic to the same value, because when n is very large, you see we are integrating, we are making this integral, and it shouldn't be very different if n is even or odd. So the idea is to prove that the ratio the ratio between two consecutive terms, so one is even and one is odd. So let's say so this is going to be so I is decreasing, so the largest one is the one, let's say I 2n plus 2. This is a general even number divided by I 2n plus 1, or make it reverse, so make it the reverse, an odd term divided by the next even term. This is we are going to prove that this is going to 1. These two sequences, they cannot differ too much, so it's not so strange that the ratio is going to 1. And this is actually very easy to prove, because we can say that this is, so we know that, remember that in is decreasing, so we can make estimates from above and from below just by changing the terms. So here, since it is decreasing, here we can put the next term, which is smaller, and here we get 1. So since it is decreasing, clearly the ratio is larger than 1. But here we can put the previous term, I to n divided by I to n plus 2. And now we know, we we know this ratio because it is written here. In divided by in plus 2 is the inverse of this fraction, so this is equal to n plus 2 divided by n plus 1. This is by this relation here. Very nice, because now this is clearly this is going to 1 and this is equal to 1, and so we have proved that this is going by the squeeze theorem, this is going to 1 as claimed. So now we can write this ratio and see what happens. I to n plus 1 divided by I to n. Okay, this is so the odd term is I1 times the next one. Here we are going to use the recurrence relation star. So I1, what is I3? I3 is from here. Okay, each term is a fraction of the previous one with the numerator, which is the term itself. So this is 2 over 3. So I1 times 2 over 3 gives I3, and if you want to have I5, we have to multiply by 5 over 4 and then 6 over 7 up to the last one is the numerator is 2n plus 1, this one here, and then numerator is 2n. Okay, while below we start from the even number I0 times, and here we have 1 over 2, 3 over 4, 5 over 6, and so on, up to the last one in the denominator is 2n, and here you have 2n minus 1. Very nice, because I1 is pi, I0 is 2. Let's check this. I1, the reverse. I1 is 2 and I0 is pi. So this is going to be 2 over pi, and now we have we put all these fractions together, and you see that the even numbers goes all on the numerator, so you have 2 times, and 4 2 times, and so on, 6 2 times, up to the last one is 2n, which also comes 2 times. And below we have the odd numbers, and the odd numbers we have 1 only one time here, the 1 only, you can see it only one time, and then you have 3 2 times, 5, and so on, up to, so you see that you have 2n minus 1 2 times, because 1 is here, and you have So let's write it on the left. And then you have 2n plus 1. Okay, so we are at the end, because now we know that this has limit 1, and so we take this on the other side, and we get that pi over 2 is the limit of this ratio, which we can write, if you like, as a... how can we write it? We can write like that. This is 2n semi-factorial. This means exactly what is the semi-factorial? Is the product of the numbers of each other factor. So this is 2n times 2n minus 2, so we skip one factor, then 2n minus 4 up to the end. Since 2n is even, the last factor is 2. And if you take an odd number, the semi-factorial is the product again of each other number. So now they are all odd numbers up to 1. And so this is 2n semi-factorial squared, and here you have 2n plus 1 times 2n minus 1 semi-factorial again squared. And this is Wallis' formula written in this formal way. Now the last part of the proof is so finding the exact value of the constant C in Stirling formula. Okay, so the idea is that we have two informations. One is that n factorial is asymptotic to this constant C times square root of n to the power n divided by e to the n, and the other is Wallis product, which is pi over 2. Let's take the square root of this one. So what we have just proven is that the square root of pi over 2 is the limit, so it is approximatively is asymptotic to this ratio 2n semi-factorial divided by square root of 2n plus 1, and here we are left with 2n minus 1 semi-factorial. Or maybe we can write it like that. I maybe prefer to have 2n plus 1 semi-factorial. So if you divide and multiply by 2n plus 1, you get here the square root of 2n plus 1. Now we want to, the idea is that in this formula here we have an approximation of the factorial depending on the constant C, and here we have an exact value depending on the factorial. So we want to plug the factorial in Wallis formula and hopefully find C. So we need to write the semifactorials with respect to the factorials. So just notice that 2n semifactorial, what is this? This is 2n times 2n minus 2 times 2n minus 4 up to 2. If you collect the 2's, so here you have n factors. So if you collect a 2, all factors are even, so you can collect 2 to the power n. You can collect a 2 for each factors, and then you are left with so you see the first factors become n, second one n minus 1, n minus 2. We are left with the factorial of n. On the other hand, 2n plus 1 semifactorial is the product of all the factors, so 2n plus 1, but you have to remove the even factors, so 2n semifactorial, and this again you can write 2n plus 1, you can write it with factorials, so this is again 2 to the power n factorial. So we have that the square root of pi over 2 is the limit of what? We have a square root of 2n plus 1, and then we have 2 to the power n factorial. Above and below we have 2n plus 1 factorial divided by, again, this term here, which is hence squared. And now let us see. Okay, now we can plug in Stirling formula. So here is 4, let's say 2 to the power 2n n factorial squared. N factorial is asymptotic to c square root of n to the power n, e to the power n, and all of this is squared. And below we have 2n plus 1 factorial, which is, maybe we can write this like 2n plus 1 times 2n factorial. So this is going to be 2n plus 1, and here we have 2n factorial, which is c square root of 2n to the power 2n e divided by e to the power 2n. Now this is equal to, okay, so you see here that 2 to the power 2n cancels with this one, okay, and so we have c squared n to the power n 2n, and below we have e, but also this e cancels, so we are left with here we have square root 2n plus 1, we have c, again square root to n, and n to the power 2n. Also this cancels, so this one cancels with this one, and so this is it. And this is, you can see also C, one C cancelled, but we are left with, if we take the limit, here we have C over, and you see that the n, so we have, let's make another passage. This is C, and here we have n divided by square root of, multiply, you have 4 n squared plus 2n, but this is asymptotic to C divided by 2. Okay, because here you divide, let's make another, you divide by n squared, so you have 4 plus 2 over n, and this is C over square root of 4, which is C divided by 2. So we find that finally C is equal to, this was asymptotic to the square root of pi over 2, and so the 2 times the square root of pi over 2, which is the square root of 2 pi. And this concludes, because this was the missing piece. So we find the Stirling approximation is n factorial is asymptotic to square root of 2 pi square root of n to the power n divided by e to the power n.